Hey, everybody. Welcome to our last class. Oh my gosh, how could that be? So, just welcome. And this has been a great class. I have really enjoyed you guys. You guys have been very engaged and working and getting most of the work done right on time. So, or close to on time. So that's really super. Somebody just joined us late. If you could put your name in the chat, that would be great. So I do ask that you complete the course survey. Thank you, Lauren. That you complete the course survey and be honest with your comments. I'm continually working and upgrading the class and trying to make it better. So your comments are very important to me. So if you could, I would appreciate that, taking the course survey. There probably are about, I think it's 786 points. I was a little unsure. But you need an 80% to pass the class. I will be sending out the certificates in early January after the holidays. So if you are so if you have a little time if you need to catch up on any back work, so it'll stay open. The class usually, well, I never close them, but I tell people that they'll be open for about a year, so you can go back and look at the material. I hope that you've been building for yourself a notebook. I'm a paper and pencil kind of person, and I think that when you're studying, if you have a notebook with all of the answers to your questions and stuff, you can go through and highlight and tab the places where you think you need to do a little extra studying. So, but if not, whatever works for you. So however it works. Here's the schedules for 2026. I sent the course syllabus for 2026. So you have a copy of that. Notice that I obviously didn't edit this very well. There we go. 2026. There we go. I don't know about this end date. I'm not sure about that. Whatever 10 weeks is. Obviously, I didn't do very good. Okay, so anyway, so those are the tentative dates. They might move a week or two one way or the other, but that's the start dates of when things are going to happen. From looking at final exams from previous classes, there are two areas where people struggle, and one is rancidity. For some reason, rancidity is just a really difficult problem for people to understand. So there are two types of rancidity. There's hydrolytic and oxidative. So in the chat, if I said hydrolytic rancidity, what does that make you think of? My dog barking. That's right, Brian and Monto, water. So what kind of foods, high fat foods, do you think there is a lot of water? What is one really good example? Maybe chicken? You're thinking chicken fat? I was thinking butter, right? So butter has water in it. Ah, tenders. Okay, but I don't think well, maybe I don't know that much about that. So Ben put in there chicken tenders. So you probably know a lot more about that than I do. So hydrolytic means that there is water and fat. So if we remember what the molecule looks like, the lipid molecule, right? Remember there are 3 carbons along here, and then there are long chains of fatty acids. When in hydrolytic rancidity, water comes in and splits the long chain from the backbone or the glycerol molecule, this part right here. And if it's a short chain fatty acid like butyric in butter, it becomes volatile and escapes into the air. So the whole thing disappears. The whole thing disappears into the air. If it is so that's hydrolytic rancidity. Oxidative rancidity. Hi, Daniel. Good to see you. Oxidative rancidity. So put that in oxidative. What does that make you think about in the chat? Oxygen. Very good.
Right.
Oxygen. So what happens is we have the same molecule, right? The same 3-carbon glycerol molecule on the back. This is only going to happen with mono and polyunsaturated fatty acids. So here's our fatty acid. Let's say it has a double bond here, and then there's more fatty acid. Maybe this one has 2 double bonds. And the double bonds are weaker than the single bonds that hold the long carbon chains together. And oxygen likes to cause problems. And what it does is it comes in here and it cleaves the molecule. So only this part of the fatty acid escapes into the air. And this is what we smell as rancidity. And this, an example of this would be any like vegetable oil or any polyunsaturated oil where you smell, or like crackers that are fried in a polyunsaturated oil. Questions about this? Was that helpful? Do you find that it is confusing, those two? Nobody wants to speak up. Everybody goes, oh, Jill, you explained that 3,000 times. We got it already, right? Well, if
I appreciate the recap, but I mean, I feel like those are pretty clearly differentiated.
oh, good, good. I try really hard because when I look at the final exams, I see that people mix these two up all the time,
Okay.
right? Yeah, that's why I went over it. Then the other thing, the other problem where I see is that people have trouble with enzymes. And I'm not going to go into it, but just to say that enzymes are proteins. And anything that denatures, changes the shape, denatures a protein is going to denature an enzyme. So things like heat, pressure, acid, salt, all of those things change proteins. They also change enzymes. So enzymes they can do good things and they can do bad things. But what it is about them is that they continue to work over and over and over again. They're not destroyed. They allow a reaction to occur at a lower temperature than it might normally. And so therefore, they may even keep going if you put the food in the refrigerator. And we could think about enzymatic browning and the avocado. And right, even though that avocado or guac is in the refrigerator, it's still the enzymes still keep working and it still keeps browning. So these are enzymes. Enzymes always, almost always, not always, end in the word ACE. So, but they are slowed, but not destroyed during refrigeration and freezing, but easily destroyed with heat. Questions about enzymes? None. Hearing none, I'll move on to some new stuff. So the learning objectives for packaging. Packaging is like if you were going to school, you would take a whole class in packaging. Right? All those different kinds of plastics and all of those different terms. don't know how much of that stuff you're going to really need to know as far as the names of all the different plastics and their properties and all that. It goes on and on and on, and they all sound alike to me. But one of the things that we can learn is when the different, when packaging, what the functions of packaging are. Yeah, I'll get it out. I'll keep going. So discuss the factors of a food product that determine the selection criteria for, and this is modified atmosphere packaging, vacuum packaging, aseptic packaging. So looking at the factors in the food, right? And then most critical properties and barrier properties. This is pretty easy, right? Metal cans, flexible pouches, glass, edible films. So the barrier properties of those. Not sure exactly what they mean. If we could think of a barrier property of a film, yes. Edible films. I don't know that that's really covered, but you know. Anyway, there is some information about that. Any questions? I'll go through some of this, not all of it, right? I also included some learning objectives that I wrote, right? I wrote these, not necessarily to be on the test, but I think that our food is primarily water. And so we need to understand how water works. So there are a bunch of terms that we need to know about water and that we can apply in different situations. So I wrote these about water, why is water important and the properties of water if we look at surface tension, heat transfer, blah, 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 blah. So let's look at, I think I just picked these ones because I think that these terms are a little bit confusing. So we're going to start with reduced oxygen packaging, or ROP. So reduced oxygen packaging includes cook, chill, sous vide, controlled atmosphere packaging, modified atmosphere package, and vacuum packaging. So reduced oxygen packaging is that whole category, not one part, right? So foods packaged to reduced oxygen packaging are considered potentially hazardous foods. And so we know that they have a pH above 4.6 and a water activity above 0.85. And they also have protein content. Any of these require a HACCP plan. So if you do any of these in your facility or in your restaurant, most health departments require a HACCP plan for these. But they're cool, right? So we can change the benefits. We can extend shelf life. We can have an anaerobic, so we can exclude oxygen. We can slow oxidative rancidity because there's less oxygen. And because there's less oxygen, we can retention of natural colors. So there's a lot of really good things. I added this to the right before class, so you don't have this part. The downside of reduced oxygen packaging is that it is an anaerobic environment. So anaerobic means in the chat, what does anaerobic mean?
No
That's
oxygen, correct?
right. No oxygen. Aerobic is oxygen, has oxygen. And we can think about this if you are a runner, right? So if you're a runner, when you run along at a slow pace, that's aerobic. You can get in enough oxygen to get to your cells and life is really good. But if you increase the intensity, you can no longer get enough oxygen into your body, and that part of your workout is anaerobic without oxygen. So then you use carbohydrates, but that's another story. So there are several micro pathogens, several pathogens that can grow with or without air. Listeria monocytogenes is special because it can grow as low as 20 degrees Fahrenheit. What's the temperature in your refrigerator?
40 or less.
Right. So that means that listeria can grow in the refrigerator. I think there was just currently a recall for shredded cheese, just the last day or two, right? So just refrigeration will not. So if you are concerned about listeria, which is always a concern for everybody, then they have to be killed during the processing process. Somehow they have to be controlled. E. coli, not till doesn't grow till 44 degrees, so warmer than your refrigerator. Clostridium botulinum, perfringens, 50 degrees, botulinum 60 degrees. So these can be controlled by in refrigeration, right? So Clostridium perfringens and Clostridium botulinum are spore forming. So with botulinum, so bot is everywhere. It's in the soil. So it's likely to be in your food, right? So the spores are harmless. We can eat the spores. But if the spore is allowed to bloom or pop open, which would be right, and then the cell inside the vegetative cell can grow, and that's what produces the toxin. It's not the spore, but it's the vegetative cells. So, and if we are ever concerned about botulinum, it's very important because you can't kill it, right, during normal processing. When we talked about retorting of low acid foods, right, we were talking about Clostridium botulinum, and we were trying to destroy the spores, right? And what was the processing? How much processing did we have to do? What is the F value for the destruction of Clostridium botulinum in a retort? Remember, the F value is your process. It's the whole process. That's right, 12D, right? So what we said is F it can be written sub-zero, but let's say 250 degrees Fahrenheit, right? F 250 degrees. And then you have your time, time, right? Your time, right? And then we want a little vague here. So 12D destruction, or 12 log reduction. So this would be the time times 12. And the reason for that is because we're trying to destroy the spore, because now we're going to store it at room temperature. And if there were any spores in there, and the spores could pop open, they could bloom, and they could produce vegetative cells. Questions?
12 log means like 100 billion, right? Like 12 zeros.
Correct. Yes, 1 plus 12 zeros, 12 log deduction. So the way the formula is really written is for 1 log deduction, and then it's multiplied times 12. So that's why it's so severe. Anybody else? Any other questions?
It's 1 plus 12 zeros behind it.
Yes.
Okay, so that's a trillion?
That means the possibility of, I don't know, what is it, Monto, trillion?
I think it's a trillion.
All right, let's say there's the possibility that one spore may exist in 12 trillion, 1 trillion
1
cans.
trillion.
Is it 1 trillion, Ryan?
Yes,
I don't do zero. I don't do that many zeros.
I just remember it from the book.
Okay, great. So that means that there's a possibility that one spore could exist in one of 12 trillion cans. Pretty safe, huh? That's what a 12 log reduction means. Okay. So if we don't do a 12D reduction, and then it's going to have to be stored under refrigeration. So all of these are stored under refrigeration. Questions? And I got this, and you can look up a whole lot more about this in the culinology text on page 248 and 249. And there are, I don't know, 10 different pathogens. I think if you know bot because of retorting, listeria because it grows in the refrigerator, E. coli because of food safety, sanitation, right? Because we get E. coli from sanitation, right? Those are probably the main ones. Um, you know, you might even, if you want to look at Bacillus cereus, if you're concerned about rice, right? Because Bacillus cereus is also a toxin, which is why there's been all this concern about the sushi rice because it's anaerobic. So you don't have to learn all of them. You might even just want to group them together. So these ones are sanitation related. So the ones that have to do with the GI tract and washing your hands and wearing clean uniforms and covering your hair and the taking your coat off before you go to the bathroom and all those kinds of sanitation ones, you can group those ones together. You can group the spore forming ones together. And then listeria, isn't that the one that grows in the drains, right? That the one that grows in your drains? So and is grows in the refrigerator. So you can kind of group them that way. So you don't have to learn, you definitely don't have to learn all the temperatures and stuff like that. Any questions? Okay.
I definitely have to revisit that the retard process because I had no idea what that number 12 meant when Brett typed that. I cannot recall that process for the life
Oh,
of
okay.
me.
Yeah, yeah. So yeah, you want to go back and look at the retort process, right?
Yeah.
So, and there was the D value, which is the time, and the temperature, which is the Z value. So be sure you know what those are. And
Okay.
then the F value, which is the whole formula.
Okay.
Yeah. So I put in my notes a couple of things like I always have trouble with the D and the Z, but time temperature. So D is time and Z is temperature. So, I didn't
Okay.
pick those names. I don't know about all that, but anyway, do the best you can.
Okay.
Okay. All right. Cook chill. Cook chill is a batch cooking method. So, which is nice. So you make a big batch of it and then you fill it hot. So according to my friend Jenny Rossoff, you have to fill above 180 degrees Fahrenheit to make sure that you've killed all of the vegetative pathogens. Vegetative means growing. Doesn't mean just living there I'm vegetating. It actually vegetative means they're actually growing the pathogens. Also, you'll kill the spoilage organisms, bacteria as well. So, and then rapid chilling and storing in refrigeration or even a little cooler, so that because it's an anaerobic environment. So, and we know that the processing is not enough to destroy the um, spores. So, because this is a pasteurization process, not a retorting process. So pasteurization is not as severe, uses the same formulas, but it's not as severe. It's not a 12D. So we know that if we have this, that we're going to have to keep it refrigerated below the 60 degrees Fahrenheit, right? So because it's an anaerobic environment and we don't want those spores to grow. So um, and I know some of you guys do some cook chill or something similar to that. So, um, and also because the food is not likely to be acidic, so it's going to have a high pH and a high water activity. So it's going to be a potentially hazardous food. Sous vide means packaged under vacuum. So you put the food in, you create a vacuum, a nice anaerobic environment, then you cook it for a really long time. Remember that pasteurization is a time temperature relationship. The lower the temperature, the longer the time. The higher the temperature, the shorter the time. You can get the same results with a low temperature and a long time as you can with a high temperature for a short time. So sous vide, cook chill is more high temperature, short time. Sous vide is long time. The disadvantage for cook chill is there's the possibility of recontamination after processing because you have this big vat and then you put it in the bag, right? So there's a possibility of recontamination. Sous vide, because it's bagged first, there's not the possibility of recontamination as long as you don't open the bag. Controlled atmosphere packaging is an active system and where you can control the atmosphere that's on the inside of the package. So generally we want to lower the amount of oxygen. So we can either do a nitrogen flush or we can pull a vacuum or whatever, or control the permeability of the package. And so that, or we could add a scavenger packet and that'll control the oxygen that's in there. Okay. Modified atmosphere packaging is where we use a gas flushing and then a sealing process. Unknown caller. Jesus Christ. Sorry. My phone rang. Jumped right out of my skin. So gas is typically nitrogen gas, which is inert. So the air around us is oxygen and carbon dioxide and nitrogen. It's mostly nitrogen. So nitrogen flush. And that'll remove the oxygen. So these two references right here, I think are pretty good. They're pretty easy to read. So you can do that. So, and then vacuum packaging. Any questions about these different processes? Anything you want to add that I left out?
Food Lord's a hell of a name.
Yeah. I looked it up. I went, really? Food Lord? Right. That's actually the name of the site. So they're pretty good references. So I checked them. And then of course your text. Does anybody want to add anything? Do you guys do any of this stuff? And how do you do it?
We had nitrogen flush in a flow wrapper. We used to package our candy in.
Okay. Did it work pretty good?
It did, but the caramels actually kind of got a little better after a while, like when they kind of ripened a little bit, but it eliminated that.
Mm,
Overall, it was a benefit though.
kind
Um,
of interesting.
mm, mm,
Yeah, Joe, Trevor and I, our Avon, Ohio facility is a cook chill facility. So we cook in 4,000 pound kettles. That's our ready to use sauce facility. We pipe it down stairs basically or over the wall and around the corner kind of thing. To large cryovac vacuum seal machines. We're not actually filling everything at 180 degrees because they were ready to use but not ready to eat, and they were being reboiled um, until one of our customers required us to do so, which was actually relatively recent. And so we've actually changed our entire process to fill at 180 degrees, and then it goes right into a big bath and it's chilled and tunneled and then frozen pretty much. So all of this is right in line with what we're doing over there.
Oh, that's super. I'm really glad to hear that. Yeah, Jenny said that people who have problems with their bags exploding and stuff like that, it's because they're
Mm.
not filling at 180 degrees and they're not destroying the spoilage
Vegetative
organism.
passages. Yeah, yeah.
Yeah. So, and the spoilage organisms are more difficult to kill than the pathogens. So if you control your spoilage organisms, chances are really good you're controlling your pathogens,
Mm,
which is nice to know, huh?
yeah, yeah,
Well, cool. Yeah, Jenny's great. She's a great resource for me. When I used to teach, I taught the food science class. The final project was a cook chill application. So
yeah,
we did that. Oh no, we just lit a little gallon in the classroom and stuff. And just a reminder, in February, the Newport Beach, the Southern California RCA is meeting with a joint meeting IFT at Jenny Rock's Village Green Foods. And it's always a fun meeting. And I think a couple people volunteered to donate some stuff to Jenny. So thank you very much. Let's talk a little bit about water. So, water is considered the universal solvent. More things can dissolve in water than any other substance, alcohol or any of those kinds of things. So it's called the universal solvent. Water activity, we've talked a lot about water activity. So it is an indicator of shelf life and food texture. Heat transfer, we'll talk about that. Sublimation is from a solid to a gas, such as freeze drying. We'll talk a little bit about expansion, conductivity. You can use water to transport your foods like, apples or produce or something through your process. But before we do that, let's just have a review. This is kind of nice. We talked about this at the first class meeting, and so here we are at the last class meeting, and hopefully it'll make more sense. But remember that what we said is that water is a polar molecule. It means it has poles, right? Like the North Pole and the South Pole. And what we know is that the hydrogen over here, the electron, the one electron that floats around hydrogen, likes to hang out over here with the oxygen because the oxygen is like the big brother. And so that means this hydrogen, this side of the molecule is going to be positive, and this side of where the oxygen is going to be negative, and that gives it poles, positive and negative sides. And so the good thing about that is that's what causes water to hang together. So when you put a drop of water on the counter, it doesn't just go like alcohol might, because it is a polar molecule. That also means that it reacts with carbohydrates and proteins, which are also polar molecules. And so the water can interact with that along with salts and stuff like that. So water is a polar molecule. Um, these molecules, they like to hang together, right? So when we have the surface of the water, there's a lot of them crowded up together. They're kind of holding it there. The pressure of the air is pushing down stronger, a little slightly stronger than the pressure of the water molecules that are floating around in here because they're mostly attracted to each other. So we have surface tension. So that's why bugs can walk across the top of the water, because there's kind of a crust of water molecules along the top. If we increase the temperature of the water, we decrease the surface tension. And so that's why hot water is a better cleaning agent or a better wetting agent than cold water, because it decreases the surface tension. It allows it to get into all the little crevices and stuff like that. There's two terms that we like to use. One is cohesion, which is the attraction between the molecules, and the other one is adhesion, or when it adheres to the sides. So I have this picture over here, this pipette, right? And the water is a little higher over here where it's adhering to the sides of the pipette, and a little lower in the center where it's not. So if we were to read this, just in case you do a pH titration, you read the bottom of the meniscus. This is called the meniscus, this little cone-shaped thing right here. So this is adhesion, and cohesion is when they like attach to each other. So I don't think I've talked about this too much, but if we talk about phase change, phase being solid, liquid, gas. So if we talk about water, water is really special because it can do all of those. It can be a solid, a liquid, or a gas. So if we look at the temperature of the water down here at 0 degrees, right there, right, 0 degrees, water goes from a solid to a liquid. And then we have what we call sensible heat. So we add for every calorie of energy, we get 1 degree of increase in temperature. So as we do that, the water increases in temperature until it gets up here to 100 centigrade. And that's the boiling temperature. And this is called sensible heat. We can sensibly see where we're adding energy, and that energy is causing the temperature of the water to rise. There's another that's called latent heat. And actually what happens when you start down here at -40, right? And then you add sensible heat and it goes up to 0. And then notice that there's this little bit of flattening of the line, and that's because it takes 80 more calories of energy per gram of water to go from a solid to a liquid. So it just doesn't happen that at zero, now it's a liquid. No, there's this intermediate phase and it takes 80 calories to change phase. Then we go up, we got all this sensible heat. And now we get up here to boiling. It takes 540 calories per gram to change from a liquid to a gas. And then once we have up here, now we have steam. And that's why a steam burn is worse than a boiling water burn, because it has an additional 540 calories in it. I'm sure you've all been burned, had a steam burn at least once, right? So that's why, because it has all this extra energy in it. So actually this down here is called the heat of fusion, and this one up here is called the heat of vaporization. When we do the other thing, when we do condensation and we go from a gas to a liquid, like condensation on the walls of your shower or whatever, this 540 calories has to be given up, and then we will go to a liquid that sticks to the side of your shower. Sublimation, which is freeze drying, is something really special. So if we make it really, really, really cold and we create a vacuum, we can actually skip the liquid phase and go from a solid to a gas, right? And that's called sublimation. And that's what freeze drying is. So if you put the food in the freeze dryer, you create a vacuum, which is the opposite of what we do in a retort. So we make it easier for the water to escape. We freeze it, we make it easier, and then we suck that water out. That is freeze drying, and that's why the freeze dried foods are nicer, because it's faster. There's less destruction of flavor, and that's also why they're kind of dried, spongy like. That's called sublimation. So this may account for the fact that, like you got the water and it's like at 100 degrees and it's not boiling, not boiling, not boiling, because it's going to take all that extra time for that extra heat to get in there so it can finally boil and that it can escape. The molecules are in the water when it's a solid are all lined up in a nice straight line. And then when it's a liquid, they're further apart and they're moving, 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 moving. And then when it's a gas, they're further apart and they're moving, 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 moving faster, faster, faster. They're moving faster. The one special thing about water is that actually when it freezes, it gets less dense. So what happens is that as the molecules line up, they form crystals and they get less dense, which you've experienced if you've frozen a bottle of water, or something, and then the cap comes off, because when we freeze it, the molecules kind of separate and form little crystals, and they are less dense, which is why ice floats. Questions? So we haven't talked about this before, but I think it's kind of important. I don't know if it'll show up on the test, but I think it's important to know. And notice that these calories here, these are small calories. They're not like food calories, which are 1,000 times this big. These are the small chemistry calories. They're little tiny. So just some terms to know. Hygroscopicity means attracting water. Deliquescence is like the same thing, attracting water. A desiccant is something that absorbs water. Let's talk about glass transition. So this one I think is met somewhere in the learning objective. What is the glass transition? That's the property of food to go from rigid to soft. So that's the temperature at which a food goes from rigid to soft. And it's called the glass transition phase. So let's say we have I don't know. I was thinking of cheese or
Jello?
Jello, maybe. Anyway, so let's say your cheese is, or your Jello is firm, or maybe we could think about like a peanut brittle, for instance, right? Or a caramel candy or something like that. And so here it is glassy state, which means solid, really, really solid. And then there's a transition when it becomes softer and softer and softer. And there's a special temperature right there. It's called your glass transition temperature when it actually goes from a solid to more of a liquid. And then we go to our rubbery flow, viscous flow. So that's what glass transition is, when it goes from a solid to a rubbery state.
When we're molding hard candies, we'll try to stay aware of the temperature where it hardens and
Yes.
keep it below that.
Mm. Excellent. Excellent. Yes. Hard candies would be a really good example of that. Right. So that temperature, or that range of temperatures, is called the glass transition, and it is abbreviated TG. And so you just need to know the definition, right? And then finally, at the last, just a little bit about dispersions, right? There are two parts to a dispersion: the solute, which is what's dispersed, right? The dispersed phase, like salt, and the solvent, which would be the continuous phase, which is like water, right? So if the particles are really, really small, like salt in water, that's a true solution. You can hold it up to the light, you can't see anything, you can't tell whether there's sugar or salt in there. That's a true solution. As the particles get bigger, there's like no magic to this. As the particles get bigger, then we have what we call a colloidal solution. If it pours, it's called a sol. If it makes a solid, like our jelly or jello, it's called a gel. If it's two immiscible liquids like mayonnaise or milk, it's called an emulsion. Butter is a solid emulsion. If it has gas, it's a foam. And a meringue is a solid foam. So all of those are colloidal solutions, which have medium-sized pieces of particles in them. And then finally, we have a suspension, and suspension is really big particles. And the best example of that is cornstarch or flour, right? So you mix those with water, they fall out. A suspension, it's temporary. they're all mixed up. Now they're all in the bottom when you go to use them. That's a suspension. So it's strictly based on the size of the particle. Questions? So we've talked about boiling point before, and remember the boiling temperature or the boiling point, right, is the place where the gas can escape. That's the boiling point. And it's a balance between atmospheric pressure pushing down on that surface, right, where all those extra water molecules are, and the vapor pressure pushing up. And when the vapor pressure exceeds the atmospheric pressure, the bubbles can escape. So changing the atmospheric pressure. So what happens, little quiz, you can put this in the thing. What happens if I increase the atmospheric pressure, or I increase the amount of pressure that's going down? What's going to happen to the boiling temperature of my liquid? Are you sure, Daniel? We'll think about that again. No, it's going to increase. If I push down, it takes more energy for it to escape, right? So think in terms of a pressure cooker. We have 15 pounds of pressure in a pressure cooker, and the temperature inside the pressure cooker is what?
250?
That's right, 250 degrees Fahrenheit. More pressure, higher temperature for more energy is needed for the molecules to escape. So let's say that I lower the atmospheric pressure. So there is less atmospheric pressure. I have a vacuum. What's going to happen to the boiling point of the water in a vacuum? The boiling temperature of the water, same thing. That it lowers. So the best example I've ever heard about this one, well, one is the freeze drying that we just talked about, but another really good example of this is when they make condensed orange juice, which is kind of becoming a relic. Now nobody buys condensed orange juice anymore. But in order so that you don't have to boil it in order to get the water to escape, they put it in a vacuum. And so that they can get the water to escape at a lower temperature so it doesn't affect the flavor. Okay? Questions?
Like a rotov
Like a who?
like a rotovap in a lab to take solvents off.
Okay. Right. It creates a vacuum, and so you don't have to boil, so the temperature isn't so high, right? So if we add sugar or salt to the water, right, it's going to increase the vapor pressure. In other words, it's going to take more vapor pressure. The water's going to boil at I think that's not right. I think this is wrong. It interferes with the water and it actually decreases the vapor pressure. You're going to have to add more heat, which is
Yeah,
why. Mhm.
if you have sugar syrup, the denser it gets, I think the boiling point increases.
Yes, yes. So that was wrong. Mark your things. Right, that's right. If you have a sugar syrup, the longer you boil it, right, the higher the temperature goes because it takes more and more pressure for the water to escape. So it decreases the vapor pressure, makes it boil at a higher, it takes more energy to get the water to escape. Whoa. All right. Questions about that? Does it make sense now? Maybe someday, right? You got, okay. All righty. I hope we're recording. Oh, yes, we are. Okay. All of a sudden I had this thought, oh my God. Anyway.
Start over.
Oh God, no. I would just put in what I did last year. Um, I think this is we're getting to the end of our time. Yeah. So just remember that the definition of water activity is because it goes back to this solution business, right? So it has to do with vapor pressure and atmospheric pressure. So water activity is the amount of water that actually escapes, the actual active water, not the total water. So be sure you understand that. Just a couple things if I can get you to stick on just a little bit longer. Because I guess I was too slow today. So when it takes test taking strategies, if you don't mind hanging in there. If you have to leave, I understand. So, and be sure whoever the last people who showed up, be sure you put your name in the chat. So the one thing, of course, is be prepared. Try and get a good night's rest. Eat a good meal that you can, right? Plan ahead. Set the date. You can always move it if it doesn't work out, but set the date. The longer you wait, the more anxious you'll become, and the you won't get any smarter, right? Read the instructions for the test carefully. Read the questions carefully and slowly, and then read the alternatives carefully and slowly. But after you read the question, see if you can come up with the answer. What do you think the answer is going to be? And then look at the alternatives. Actively reason, anticipate your answer. Oh, yeah, Anna wants us to take a picture. Okay, I'll do this quick, Anna, before everybody leaves. Okay. And you could read the rest of this yourself. Anna wants a picture if it's okay with everybody. So just one thing, if there's two that are really close together, it's probably not them. Sometimes the longest one is the right, but you can read all of this and but just take your time. All right, Anna, if we could get everybody to turn, I'm going to